Hi, I'm making this video to give you an oversight into the big picture of what calculus is about. I find that many students who are coming into calculus really don't know what it is that they'll be studying over the course of the year. To be honest with you, if you talk to people who went to college and took calculus and passed calculus and graduated and went on with their lives, they might not know quite so much what calculus was about either. But I have a theory that people enjoy the course more and do better in the course and will have fonder memories of the course if they have kind of a map they can check back with at the beginning of the year or maybe throughout the year. So let's see how popular this video is with you. I just want to give you a little bit of a heads up of something I'll do when I make videos. I've got this little chime here. So when you hear this sound, that means that the question that I just asked was not rhetorical. That if you wanted to, you could pause the video and think about it. And it would either, sometimes the question has an answer, which could be right or wrong. Sometimes the question is open-ended and maybe doesn't have an answer. But the concepts that you're thinking about during that time will spur the future discussion. All right, so let me share the screen here. This program is called GeoGebra, and it is an online graphing calculator, and it's pretty awesome. You'll see me using them a lot over the course of the year. I might have you using it from time to time. I'm not really sure. We'll work that out as we go along. At any rate, there's a line graph here on this coordinate plane, and I want you first to tell me what the slope of this line is. Well, as you probably remember from Algebra 1, the slope of this line is 2 over 1. And you could think of that by starting from this point and going up 2 and over 1 to get to point D. Or maybe you started from this point and went up 2 and over 1 to get to point E. Or maybe you started from point C and you went up 4 and over 2, and you realized that 4 over 2 could be simplified as a ratio to 2 over 1. The moral of the story is that since we have this line, it really doesn't matter what 2 points you use to establish the slope. One phrase you might have remembered us using a lot back in Algebra 1 is that a linear relationship depicts a constant rate of change. And you might have heard us say constant rate of change, constant rate of change, constant rate of change over and over again, and not realized quite why we were so insistent on the importance of that fact. But let's move on to a second example here. So let's take away this line, and I'm going to put in this parabola instead. Now, what if I asked you what the slope of the parabola is? What do you think you would say to that? Well, when I asked a student a few days ago, that student said, well, the slope of this is 3 over 1. And I said, what led you to that conclusion? And the student said, well, if you go from here, you can go up 3 and over 1, and you have both points on the line, so that must be the slope of the parabola. And that was very well observed. The slope between those 2 points is 3 over 1. But I said, what happens if you go over here and we go from E and we go to point F? Now we're going down 3 and over 1. So isn't the slope there negative 3 over 1? Or what happens if we go from F to C? There we're going not up or down at all, just over 2. And so the slope there would be 0 over 2 or just 0. So sometimes when we pick 2 points on this parabola, we're going to have a positive slope, sometimes a negative slope, sometimes a 0 slope. That's a very different situation than we had with the line. The line had a constant rate of change, which means no matter which 2 points you picked, you would get the same slope. A parabola, and really any other shape other than a line, does not have a constant rate of change. It depends which 2 points you're measuring from. And that makes this notion of the slope of a parabola a much more difficult concept to think about. But still, it's something that we do think about. It's an important question for us to be able to ask. It has lots of applications in science and engineering, and as we've talked about, lots and lots and lots of other professional modern 21st century fields. So let's give a sense of how we tackle this question. What we just talked about with taking 2 points and finding the slope of the line segment between them, we'll call that the average rate of change. We're going to add a new concept in calculus, which we're going to call the instantaneous rate of change. All right, so I'm going to pick a single point there, right there at 1, 1. And you can see that this is curved here. There's not a straight line that you can measure along here. But if I start to zoom in a bit, this curved section is looking more and more like a straight line, isn't it? If I contrast it to a straight line, you can see that it starts to veer away when we get to the edges, but boy, it's pretty close. And when we zoom in even further, now you really can't tell the difference between the straight line and the parabola when we're zoomed in this far. So at this point, now that this looks essentially like a straight line, we could talk about the slope of any 2 points near this 1 point that we were talking about. And just like we had with the original problem with the line, the slope of this is 2 over 1. So based on that, let me put this line back up and we'll zoom out and you'll kind of see what that line looks like in relationship to the parabola. So just like we had tangent lines in geometry, which was a line that touched the circle only in 1 point, we can kind of think about tangent lines to other curves that only intersect in 1 point or near that 1 point. All right. And when we've got a tangent like that, we can think about the slope of that tangent line, and we will call that the instantaneous slope of the parabola. So at this point in the parabola, it's growing at a rate of 2. And what we'll formally say is this is an idea in calculus called the derivative. And so based on that, we will say that the derivative of the function y equals x squared, when x is equal to 1, that derivative is equal to 2. All right, and that's something that's very based on that point. If I pick another point up here, maybe I pick this point right here and zoom in. Once again, it's going to look very much like a straight line, but the slope of this straight line isn't 2. The slope of this line is 4. All right, so the notion of a derivative is something that we will spend a lot of time focusing on over the course of the year. In fact, Unit 2 of our 5-unit course, Unit 2 is going to be defining the derivative and finding the derivatives of lots of common function families that we've dealt with in Algebra 1 and Algebra 2, like exponential functions, trigonometric functions, polynomial functions, and so on. And then in Unit 3, we're going to use applications of the derivative. We're going to find real-world problems that we're going to be able to solve by taking advantage of this derivative concept. Even problems where you would look at it and you would think this really isn't about slope at all. But we are going to find that knowing about the derivative is going to make that problem easier. All right. The second major problem that we address in calculus is, let me highlight this right here. All right, so I've got this shape right here. It's not quite a triangle, it's 2 straight lines, line segments. And then the third side is part of the parabola. And the question I want to ask here is, what is the area of this shaded figure? All right, once again, we don't have any tools that we've learned up to this point that are going to help us to answer that question. We know how to find the area of circles and triangles and rectangles and trapezoids and lots of other common figures, but ones that have weird curves like this, we don't have any tools for taking care of that. And so this is the second major problem that calculus addresses. And let me give you, again, some basic sense of how we're going to address that. let's say that I take this line segment right here, and I say that the area of this triangle is an estimate of the blue shaded area. Okay, it's too big, but it's better than nothing. It's a good start. Okay, or I could have a slightly better estimate. Instead of taking that triangle, I could take the area of this trapezoid here on the left. Remember, a trapezoid is a quadrilateral that has one pair of parallel sides. Whoops. So this vertical line and this vertical line are parallel, so that's a trapezoid. We can find the area of this and then add to it the area of this triangle. Once again, that's going to be a little bit of an overestimate, but it's going to be a much better estimate than the original one triangle. See, there's this whole area that we're carving out. So our estimate is going to be better using two shapes than one shape. And you might guess again that if we zoomed in even further, sorry about that, if we zoomed in even further and took 4 shapes or 10 shapes of trapezoids and triangles put together, our estimate is going to be better and better and better because of it. And let's just say that if we took enough shapes, we would have a very, 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 very close estimate. We can get an estimate that's as close as we want. And this is a notion in calculus that's called the integral. So when we were solving the slope problem, the answer was going to be what we're going to call the derivative. When we're solving this area problem, the solution in calculus we're going to call the integral. Those of you who had me for geometry, you know that I am very proud of the fact that for the most part in math, we pick good names to go along with our math concepts. Words that make you think, oh yeah, that word reminds me of this math definition that you want me to remember. Derivative and integral are both horrible names in that respect. I'm sorry about that, but we're just going to have to lean into it because we didn't get a vote when we made these words. So unit 4 of our course is going to be defining the integral. Once again, taking the integral of lots of functions that we are familiar with over the years. And unit 5 is going to be using applications of the integral. So I have talked about units 2, 3, 4, and 5. That leaves unit 1, which I haven't discussed yet. One of the things you may have noticed or felt about when I was talking about these two problems is that I'm being a little wishy-washy when I'm talking about these definitions. When I talked about the derivative, I said if you zoom in enough, this is going to look like a straight line. And you may think to yourself, what do you mean by enough? What do you mean looks like a straight line? And when I'm talking about the integral, I'm saying that if you use enough shapes, you're going to have a pretty good estimate of the area. And you might respond, what do you mean enough shapes? And what do you mean pretty good estimate? And these are both wishy-washy explanations that I gave that are going to be much more clear when we give the definition of a new concept called the limit. The limit is as much of a new thing that you've got to absorb to get used to calculus as when you learned pre-algebra and you got used to the notion of variables. So a variable was some number, and you were using this letter symbol to stand for a number whose value you didn't know. And that was weird when you first got to it, and it took a little bit of practice to get used to it. But once you did, you noticed how powerful the things you can do in algebra were. This is the same thing happening here at the beginning of calculus. We're going to define the limit, and it's going to be something that takes a little bit of getting used to. But once you get it under your belt, we're going to be able to tackle these definitions of derivatives and integrals in a really precise way that let us really get into these situations and solve these very important questions that have lots and lots and lots of applications in the scientific, engineering, financial, humanities world that we live in at this point. So hopefully that gave you a good preview of what our class is going to be like, what kind of things we're going to be doing. And as the year goes on, maybe halfway through, you're going to come back and you're going to look at this video again. And you're going to say, oh, we've made a lot of progress here. I really understand that slope problem now that we are in November or something like that. Or, you know, when we get to March, you're going to start to understand both of those situations very well. So hopefully this is helpful to you, and we'll just leave it at that.